Okay, so thank you everyone for coming, and welcome to this second seminar in the PMIP Wings series. This is trying to be a roughly monthly set of talks, sort of collecting together the paleoclimate community. And the way we're going to set this up is we're going to have two talks by two different speakers, and then hopefully they'll both last about 20 minutes, leaving us for some time for some discussion after that. If you have questions that you want to sort of raise, pop them in the chat. We can have a bit of a chat going on whilst people are talking, and then we can pick up questions at the end and have that discussion. I ought to have introduced myself. I'm Chris Briley from University College London. So that's that done. On my list, on my notes for what I'm supposed to say at the beginning of these seminars is that everybody should be using, it would be helpful if everybody uses a proper name. And thankfully everybody already is doing that, so having their proper name. So that's that. And the next one of these seminars will be on the 30th of March at 9 Universal Coordinated Time, which will have some talks by Zhongshu Zhang and Shiling Ho, and that's going to be led by Masa Yoshimori, but there'll be more discussion about that later. And so I think that's probably all I wanted to say at the beginning. And with that, maybe I can pass on to our first speaker, which is going to be Charlie Williams. And Charlie has been involved in PMIP for quite some years now, both at the University of Reading and the University of Bristol. And he's been the real, I suppose, the main representative of the UK climate communities who've actually run some paleoclimate models and contributed to the new round of PMIP4. Certainly I've been involved in PMIP and have not run any of these simulations myself. So it's down to Charlie doing this work that's really quite important. And so what he's going to talk to us about is some of the lessons that he's done, he's learned having run these models and the science behind it. And so maybe I can pass over to you, Charlie.
Yeah, okay, I will just share my screen. Hopefully you can see that. Let's go into presenter mode.
Yep, that's working well. I can see that.
Okay, yes, well, thanks, Chris. So, as we said, I'm Charlie. I am a research fellow at the University of Bristol. I'm just going to turn my camera off to save on bandwidth, but hopefully you can still hear me. So today I'm going to talk about HADGEM 3. Now, I've changed my title a little bit from what was advertised, in that I've removed the word warm, simply because I wanted to talk a little bit about our LGM runs, and as we know, it wasn't exactly warm during the LGM. So it's really looking at all of the HADGEM 3 paleoclimates. And I should make special acknowledgements to Victoria, Kenji, and Seb, who, with my help and input and assistance, have actually either run some of the simulations or are currently running them at the moment. So I'm going to give a very brief introduction to HADGEM 3. I will try and keep it brief because I know that a lot of you probably know all this. Then I'm going to give a brief overview of the various simulations. Now, I've ordered these according to not time period, but according to complexity, if you like, technical complexity in terms of actually running them. Then I will finish with some of the lessons learned and some reflections of using this model. So you can see here on the right, a very simple diagram showing the primary resolution differences between the older version of HADGEM 3 and the new HADGEM 3. The take-home point there is its finer resolution in virtually all dimensions: atmosphere, spatially, horizontally, and the ocean depth. So, Gem 3 is a fully coupled GCM from the UK Met Office Handy Centre. It is the physical model of the UK Met Office Earth System model, UK ESM1, and there are various versions, all based on different atmospheric and oceanic resolutions that you can see here are coloured in red and blue. We are using the first, Gem 3 GC31LL, which has a resolution of N96 in the atmosphere and a 1 degree ocean in the ocean. As I said, I'm going to be quite brief about how much detail I go into. A, because a lot of you know already, and B, because it's been published extensively in Williams et al., which is not me, by the way. That's not me, or Till's work. And the model has been used extensively in CMIP 6, especially the historical and PI control simulations, and there have been a raft of other studies that were all published a few years ago in a special edition of James, looking at various things like climate sensitivity or feedbacks or ozone or aerosols. So in this version of the model, it's exactly the same as the version used with the CMIP 6 PI control. So we are using, as I said, an N96 spatial resolution. We're using a Nemo ocean with a 1 degree resolution. We're using the global sea ice, version 8. We're using Jules as the land surface model, and it uses the Oasis 3 coupler. And the full title of this, as you can see here, is a bit of a mouthful. So we generally refer to it as Gem 3. And the various individual components summarized by, again, not by me, by another Williams, is detailed by various companion papers. Again, I'm going to skip over this quite quickly because it is being recorded, so you can come back to this if you want to. But basically, there have been a number of improvements since the previous version of the model, GC2, either in the atmosphere, such as to the radiation scheme or to the warm rain, etc., and in the ocean to remove certain biases. And what this resulted, compared to the previous version, is that they and I was not involved in this, managed to reduce various model errors, such as to the South Asian monsoon and to biases over temperature, and so on and so on. So there have been a number of improvements since the last version. So on to the paleoclimate simulations, which is what we are here to talk about. I've classed these as, well, I've used the word orbital just to categorize them, really. There were more things changed than just the orbit, but given that they both are comparable, I've called them the orbital simulations. So first we have the mid-Holocene, and second we have the link. So Victoria ran the link, I ran the mid-Holocene, and then I compared both. And what we did was we changed only really two things, which is why I'm starting with this, because it is probably the simplest simulation. First of all, we changed it all to orbital parameters, and secondly, we changed the CO2 and other greenhouse gases. So to give you an example, the CO2 in the PI was 284 ppm. The mid-Holocene was a bit less, at 264, and the link was a bit higher at 275. And this was in line with Betty's experimental design paper. All other boundary conditions and initial conditions were kept the same as in the PI. So you can see some examples of these here. And what we did was we started at the end point of the PI control, about after 600 years, and then we ran the models, the model for 400 and about 400 years for each, with the final 100 years being used to calculate the results. So what you can see here is the TOA radiation balance on the left, and the ocean temperature, the full depth ocean temperature on the right, where you can see that by the end of the entire simulation, we are getting a TOA balance, which is approximately trending towards zero, and likewise a mostly equilibrium state in the deep ocean. So to show you some of the results quickly, the top panel shows surface temperature for calendar adjusted June, July, August, so northern hemisphere summer. To the left on the mid-Holocene, right the lake, and the bottom is precipitation. And what you can see here in general is that both simulations are behaving roughly as expected, i.e. we have warmer summer temperatures, precipitation increases, especially over North Africa, more so in the lake than in the mid-Holocene. Compared to proxy data that I'm not showing you here, both simulations are more or less capturing the sign and magnitude of change. There is some geographical variation, but more or less. When I compared this to previous versions of the model, there was, in some instances, a clear, obvious improvement. So if we look at mean annual precipitation, for example, HADGEM 3 is a lot closer to the proxies than, say, HADGEM 2 or HADCM 3. However, when we produce this figure, which is to address the ongoing question of Saharan greening, which I know Peter Hopcroft has done a lot of work on recently, we can see that with the current setup, HADGEM 3, which is the thick black line, is still not really reproducing the amount of rainfall needed to support grassland that the proxies suggest. So, moving on to the mid-Pliocene simulation. This was slightly more complicated because it requires a lot more things to change. So we changed the CO2, for example. So all of these were following Alan's experimental design. And we changed the CO2 to about 400 ppm. Well, not about, exactly 400 ppm. With all the other greenhouse gases kept as in the PI. Ozone was taken from a one-time CO2 simulation using UK ESM1 at an appropriate temperature, and then orography, ice mask, vegetation, etc. The only deviation from the experimental design paper was the land sea mask, which I kept as PI for reasons that I will explain a bit later. And so you can see here the full 600, 500 year simulation, where you can see I incrementally add in each Pliocene modification. And so you can see a steady warming as we introduce the ozone, topography, and ice mask, and then a rapid warming as we introduce the vegetation. And that is a topic of ongoing work at the moment to address why that might be. So here you can see surface temperature. Again, anomalies, so the Pliocene versus the PI. And again, what you can see is that as we would hope, in line with what we would expect, the simulation is showing warmer and indeed wetter, I haven't shown you that, but and indeed wetter conditions, with the greatest warming occurring over polar regions. By the end of the simulation, the end of the Pliocene, it was 5.1 degrees. The anomaly was 5.1 degrees above PI, which is the second highest of all the models that were used in Climate 2. If we then look at a comparison with previous model generations, you can see here different SST maps. The first three are showing HAD-CM3 with slightly different configurations. Then D is showing HAD-GEM2, and E is HAD-GEM3. And finally, the global annual mean anomalies in temperature over all climate models. So what you can see is that firstly, there's a clear warming increase in SST as the model has been developed. But up to a certain level of warming, this appears to agree better with the proxy data. In fact, the sweet spot appears to be HAD-GEM2, i.e. HAD-GEM3 is too warm. And this is further confirmed when you compare it to other Climate 2 models, where HAD-GEM3 is by far one of the warmest and wettest models of all. So we now go to our cold simulations, the LGM. This was more complicated still, primarily because it involved a change to sea level and therefore the land sea mask. So what we did, again, according to Master's experimental design paper, we changed things like orbital parameters, changed the greenhouse gases. So here the LGM was 190 ppm, and we used the ICGC reconstruction for the ice sheets and the land sea mask. And again, what Henry did was he introduced the various forcings incrementally. So he started with a PI land sea mask in the red line at the bottom left, before moving slowly to a full LGM simulation involving all parameters, gases, and land sea mask. The difference between the light blue and the dark blue lines is that the light blue contains a previous topography. So from previous simulation, PI simulation, topography over Antarctica, so 60 to 90 degrees north, whereas the dark blue is fully LGM. It's still running. So again, it was started after the PI. It's about, in total, it's about 500 years in. But if you only consider the true fully LGM simulation, it's about 100 years in. It's 200 years in. And what we can see, even at this stage, is that as it's coming to the edge, the two blue lines are firstly very similar, and secondly, have flattened out. However, looking at the TOA on the right, we see that it is still trending towards a negative balance, and so it probably needs to go a little bit further. There were some very early results. Now, these were taken over the last 50 years of the simulations, 150 years, 50 to 100 years. You can see that on the top we have temperature, and on the bottom we have precip. On the left we have HAD-GEM3, and on the right we have HAD-CM3. And really the sort of main point is firstly that the spatial patterns of temperature are quite similar, although there is more cooling in HAD-GEM3, especially over large land masses such as Africa. Likewise, for precipitation, there are some similarities, but in general, HAD-GEM3 appears to be a bit drier, such as over the Amazon or the Western Indian Ocean or the Northwest Pacific. If we compare this to proxy data, where we are using two different types of proxies, a previous round based on the Bartline et al. And the Margot data, And then the more recent reconstructions based on Pierre et al. And Clearton et al. What we see, if I circle the HydGem3 results, these show the yellow and dark blue lines that I showed before. What you can see is that it's clearly warmer than some of the HydCM3 simulations, which are the other dots, but still a bit too cold compared to reconstructions. So lastly, looking at the very warm simulation, the early Eocene, this was by far the most complex one to set up, primarily because it involved quite a large and significant change to the land sea mass. It followed Dan's experimental design as close as possible. So again, we changed things like greenhouse gas, aerosols, ozone, the orography, river runoff. That was a particularly nasty job to do because a brand new river map had to be created based on just the topography from Herald and changing some additional conditions to better represent a early Eocene starting point. At the moment, it's about anywhere between 100 and 400 years into its run, depending on which CO2 you're talking about. So, for example, the one-time CO2 simulation is about 450 years in, whereas the four-time simulation is only about 100 years in so far. Nevertheless, it is actually running, which is a massive start. What you can see here is some very early results. So the top left is the temperature, the bottom is the TOA. And what you can see is that even the 400 CO2, the red line at the top, is roughly stabilizing, even though the TOA balance is still very negative, but is nevertheless trending in the right direction. And so hopefully soon the others will also be near to equilibrium. When we look at some spatial maps over the last 30 years, we can see that firstly, at higher levels of CO2 are obviously a lot warmer, especially at 3 times and 4 times. They are partly capturing the reconstructions, such as in the Southern Ocean, but less so elsewhere. And indeed, less elsewhere, such as in the low latitudes, we are seeing that the 1 time and the 2 times CO2 are actually a little bit closer to the reconstructions. This figure was taken from modified from Dan's paper and shows the deep MIP ensemble. So all the models that did the early Eocene simulation, where you can see the temperature on the left versus the CO2. And the grey box shows you the proxy data boundaries. If we then add in the most recent CESM2, which came after CESM1, which is included in these grey dots, you can see that firstly it is way too warm, even compared to its predecessor, and temperatures higher than all the other ensembles, especially at 3 times CO2. So the question is, where does HydGem3 fit on this figure? The answer is here. So as you can see, even though arguably it's not quite in equilibrium, you can still make the comparison and you can still say that although it is warmer than CSM2, than the other ensemble members, it is still a bit cooler than CSM2. So, I learned a lot of lessons doing this. Here are just a couple. The first is the land sea mass. These changes turned out to be extremely non-trivial and is a complicated process that I won't go into now. Essentially, a bit of it can only be done at present within the Met Office firewall. We are hopefully trying to change that, but at present, that is true. Secondly, there was a code change. So what felt like forever, I continually got a atmospheric blow up in different parts of the world, always usually near the higher latitudes, which always happened almost straight away. And I tried various different tests. I tried incrementally changing from PI to Pliocene, country by country almost. As it turned out, the problem was resolved by making a very small code or parameter change within the model code, and in particular, to those dealing with snow cover on the canopy layer. And basically, the issue was, as you can see here in the top right-hand corner, the PI, and the bottom of the Pliocene, I was really increasing the broadleaf trees and needleaf trees in high latitudes. And what that meant was, because of the increased snow, it was unrealistic buildup of snow, and so it was blowing up. Lastly, we learned a lot about the ozone. So at the moment, in my Pliocene, I took ozone from another UK ESM simulation. However, what we are now using, and I say we, because somebody did all of this, is interactive ozone. And what he found was a major problem when you use this ozone remapping at very warm climates, such as the Eocene. So you can see here, the pink line shows the tropopause height, which you can see is fine at 1 times CO2, but then goes weird at 4 times CO2, and likewise for the other higher simulations. You can see it's basically here. It looks fine, the tropopause between 1 time, but then goes really weird at 4 times. And what he found after much digging was that this was all to do with the definition of the tropopause height, which I won't go into now, but long story short, when he corrected it, we got a much better looking tropopause regardless of CO2. So in terms of some reflections, we all know it has very high climate sensitivity. We all know that it's one of the highest in CMIP 6. It is the highest in PMIP 2. And so that makes, I think, it interesting to look at these very warm or cold climates. It's also very sensitive. So those of us at Reading used to lovingly refer to HAD-CM3 as the bomb-proof model because it would run under virtually any conditions. HAD-CM3 is not like that. HAD-CM3 will crash at the slightest, tiniest error, and so it is very technically sensitive. And lastly, of course, there is a speed and resources problem. HAD-CM3 is very slow. Faster models like HAD-CM3 can do 80 to 100 model years per day. We are getting about 5 or 6 per day. And because we have to use the central supercomputing infrastructure of Origin 2, you can see here, the blue, this is as of yesterday, the blue is the nodes being used, pink is the nodes reserved, and only orange, right at the very top, is nodes available for use. So there is a speed and resources problem. In summary, it's the core of UKSM. It is very capable of doing these simulations, despite various challenges, and I believe it is worth using because of its high sensitivity. So here are the references, you can read them later, and thanks very much.
Thank you very much, Charlie. I think what I'll do, if that's all right, is I'll let people put any questions in the chat, and then if we pass on to Ran.
Yeah, sorry, I ran over a bit, sorry.
That's fine, don't worry. And then we'll take any questions at the end if there's time. So can I, without much further ado, can I pass over to you, Ran, and get you to share your screen?
Yeah, of course.
Thank you very much.
Right, let's swap display. Okay, great.
Oh, so we can see your presenter's view now.
Oh, wait.
I'm afraid.
Sorry about that. There should be a button swap display somewhere. What about now?
That looks good for us.
Apologize for
That looks fine for us at the moment. I think we're seeing what you're seeing.
But this doesn't work.
And that's now showing us the presenter view. Is there a way you can be brave and do it without seeing your notes?
I could. Let's see. I'm surprised there should be a swap display somewhere. Did you see it on your screen? No. It was there.
No, I mean, I can't see it here. There's a screen one, but I mean, that's looking good for us. What I'm seeing. I guess that's
okay. I'll just have to have a go with it. All right. Yeah. Hello, everybody. Thanks for participating in this seminar. Today, I would like to share some of our results on the mid-Pliocene hydroclimate changes we learned from the Pliocene modeling comparison project 2 simulations and some of the new sensitivity experiments. Before I start, I would like to acknowledge my co-authors who are the PMIP 2 participants who made their data and available and also contributed a lot to this the discussion of this paper. So I'm very grateful to all of them. And I also would like to acknowledge my co-author, Tripti Bhattacharya, who actually compiled the proxy hydroclimate indicators that you all see in this talk and devised the method for data model comparison. Right, I would like to quickly mention why we're interested in those past warm intervals. To the left here, this is a chart of estimated global mean temperature and CO2 for the past 100 million years. As you can see, those past intervals, warm intervals, including the mid-Cretaceous, early Eocene, Pliocene, and they sort of kind of match the concurrence of those high CO2 intervals, and a lot of them have warming magnitudes that are comparable to the projected future warming following different socioeconomical pathways. So by studying the past warm intervals, hopefully we can learn some insights for future climate change. I would also like to mention the framework of thinking about past warm intervals. I think we have to pay attention to the timescale of climate responses to increasing CO2. So from in the short timescale, from years to decades, the responses involve clouds, water vapor, snow, and sea ice, so as well as our ocean heat content. So the fast responses. However, when we think about those past warm intervals, our climate forcing actually comes from long-term responses as well, including changes in the biome range, ice sheet, wax and wane, associated changes in ocean circulation. So typically when people think about the future climate, people only mainly thinking about the relatively fast responses. And this is also something taken into consideration in like estimate of equilibrium climate sensitivity. However, for long-term responses, the responses that are particularly relevant to those past warm intervals, like vegetation, ocean, three-dimensional actually, those also contribute to shaping those past warm intervals. And in addition to the short-term responses, those long-term responses are something termed as part of the Earth system sensitivity. So in this particular study, we're particularly interested in how those long-term responses can actually help shape the hydrological state in the northern subtropics during the mid-Pliocene, which is roughly covers the 3.0 to 3.3 million year interval. And for this particular study, we're taking a regional perspective to look at hydroclimate changes. And the reason for that, I quote from the US National Science Foundation Palaeoclimate for Future Climate Change Program, is that regional and short-term variability is often very different from the long-term global changes. However, people in society experience climate change most directly at a regional scale. And this is especially the case for terrestrial hydroclimate trends and changes and variability. So this map to the top shows the precipitation minus evaporation changes following the RCP 8.5 across the ocean. And you can see this very typical wet gets wetter, dry gets drier response with wetter tropics and drier subtropics across the globe. However, if we focus on the terrestrial hydroclimate, you'll see this heterogeneity. There's no clear indication of subtropical drying versus the tropical wettening. And this has a lot to do with changes in the warming pattern on land, as well as the regional circulation changes. One of the most intriguing features from the compilation of mid-Pliocene reconstructions is this northward and westward expansion of over regional trends of continental greening at the expense of the desert. So those two maps, the top shows the present day soil types, and the bottom shows the soil types reconstructed for the mid-Pliocene. And the magenta circles here highlighted the dry land soils, antisoil and radisoil, and you can clearly see the shrinkage of desert and dry soils from the East Asia and from the North Africa. Similarly, we also have vegetation changes that are consistent with this changes in the soil types. From the top shows the present day distribution of the biome types, and the bottom one shows the Pliocene. And I highlighted here are the dry, temperate, and tropical shrubland, as well as desert type of biome. And again, you see this similar westward shrinkage of dry land from East Asia towards the Central Asia, and you see this northward shrinkage of the dry land in the North Africa. So how well do the PMIP2 simulations simulate those wet conditions? Here we devised a way to quantitatively assess the model behavior. And because of the sparsity of quantitative precipitation reconstructions, we relied on the qualitative hydroclimate indicators. So the sites are showing here in this map. So those are pollen record, lake record, sedimentary records that were based on the interpretation of the original publication. They either indicate weather conditions compared to the quaternary or the present day, or neutral or drier conditions. And we applied a age filter. So we only selected the records with reported age constraints that overlap with this 3.0 to 3.3 million year interval. In order to perform a categorical correlation, we converted the model simulated precipitation minus evaporation based on a range of threshold or percentage precipitation minus evaporation changes. So at the site in the model simulations, we categorize the simulated state as being wet, neutral, or dry based on the thresholds. This map shows the calculated GWATS AC, which is the categorical correlation between the proxy indicators and the model P-E changes. And the y-axis shows corresponding to a range of threshold. We tried the threshold from 5% all the way to something like 80%, and y-axis shows the model behavior. And in general, lots of models actually show the reasonable scale at reproducing the weather conditions recorded at those proxy sites. There are models that are particularly skillful, especially the Easy Earth 3.3. There are models that are relatively less skillful, such as the NOR-ESM and the GISS model. In terms of multi-model mean, below a threshold of roughly 30%, the models generally can match the proxy hydroclimate indicators. It's also very interesting that we noticed the model behavior or the model skill at reproducing those hydroclimate indicators scales more strongly with simulated global mean warmth for the mid-Pleistocene, showing the top panel here, but less so with the equilibrium climate sensitivity of the models, which is showing the bottom panel here, which suggests to us is perhaps this additional amplification, warming amplification factor due to prescribed boundary condition changes are actually more important than just the direct CO2 effect in simulating the weather conditions in this region. So use the Community Earth System Model version 2, CESM2. I carried out a series of single forcing experiments to quantify the contributions from prescribed mid-Pleistocene CO2 and other boundary conditions. Here are some results from the single forcing experiments. So they essentially substitute one aspect of changes, either CO2 or some boundary conditions in the set of simulations. So by quantifying a pair of simulations, we can single out the effect that are attributable to an individual forcing. So let's take a look at the CO2 first. In general, so to the left here, this is the response, P-E response to CO2 forcing with Pleistocene geography and topography conditions. And to the right here, that's the response of CO2 again, but with pre-industrial geography and topography conditions. And the top panel here shows the full response. You can see that across the areas that we're interested in, North Africa and East Asia, CO2 contribute a moderate amount of wettening in the East Asia, but not so much in the North Africa. There is a small, or there is a moderate state dependency on the geographic and topographic conditions of CO2. But generally it doesn't change our assessment that the CO2 only played a minor role or secondary role in driving the P-E changes we're seeing in the full forcing experiment. Those two panels here shows the effect of prescribed geography and topographic conditions and the effect of vegetation ice sheet. And you can see that the geographic topographic conditions seems to contribute moderately to the wetting in North Africa, but it's really the prescribed vegetation ice sheet conditions that that are able to reproduce the majority of the full forcing experiment, full forcing response. We also looked at the contributors in terms of dynamic processes to the P-E changes for the North Africa or Sahel region and the subtropical East Asia region. We split the P-E changes through a moisture budget analysis into the contributions from the tropospherical moistening, stationary wave changes, zoonotic mean circulation, and the nonlinear interaction between circulation and the moisture. So here, stationary wave is used to refer the regional departure of circulation changes from the zoonotic mean. So it's clear that you can see the ensemble experiments, the partition of P-E changes is consistent across the ensemble experiments. The CSM2 full forcing experiments and the CSM2 just forced with Pleistocene vegetation ice sheet changes. And the other feature you can see is for both regions, the key processes that driving the positive P-E are tropospherical moistening and the stationary wave responses. We can further link those changes to prescribed vegetation ice sheet changes. So to the left here shows the dominant plant functional type for each grid cell prescribed in the CSM2 for our PMIP2 simulations. The most striking feature is probably the continental greening all the way across the northern highlight shield, as well as in the Central Asia and the Sahel region. And consistent with the prescribed vegetation changes, we do see a strong increase in the latent heat flux across these regions, suggesting an enhanced evapotranspiration by through continental greening process. This contributes to the tropospherical moistening. In addition, in those experiments with prescribed vegetation ice sheet alone, we also simulated a substantial amount of warming, actually half of the warming of the full forcing experiment. With the warmer surface and warmer troposphere, we also have this additional increase in specific humidity in the troposphere, contributing to an enhanced tropospherical moistening process. Besides the effect on the evapotranspiration and surface energy partition, prescribed vegetation changes also induces a regionally enhanced response of surface albedo. So all those regions with substantial continental greening showed a much stronger reduction of surface albedo compared to the surrounding regions. And this generated a interesting warming pattern. So places with a strong albedo reduction generally featured more warming than the surrounding regions. And we think this warming pattern actually generated a stationary wave pattern. This map here shows the 600 hectopascal stream function difference through between the mid-Pleistocene and pre-industrial, and this is the wave number 1 through the Fourier analysis. And you can generally see that the wave centers located in the Atlantic Ocean, the northern and the tropical side. This rotational wind following those wave centers generally follows the thermal wind relationship with respect to the surface horizontal gradient of the warming. And following the southern branch of this wave center, You can see an enhanced inland moisture transport from the tropical Atlantic Ocean and as well as from the Indian Ocean towards North Africa and the East Asia region, which is consistent with what we see in this strong P-C increase due to the stationary wave or regional circulation changes. Just a quick conclusion. So what we find is that model scale at simulating weather northern subtropics scale strongly with simulated global mean warmth of the mid-Pliocene, less so with equilibrium climate sensitivity. And this highlights the importance of long-term vegetation ice sheet response to CO2 in shaping the terrestrial hydrological cycle. And continental greening contributes to wetter Sahel and East Asia in our analysis, mainly through two processes: enhanced warming and evapotranspiration, as well as the generation of regional warming pattern resultant stationary wave pattern. It's interesting that when you think about continental greening, it's actually underway, but mainly through the CO2 fertilization process. This map here shows the trends of growing season leaf area index from observed from 1980s to the 2016. However, when we're looking at shorter time scale climate contributions to this, it's actually very complex, and a lot of places the climate change actually contribute negatively by enhancing the drought frequency and intensity. But perhaps based on our reconstructions, past reconstructions, we might be expecting a long-term positive feedback from climate change to the vegetation growth, and especially at places where we have the strong record showing the wettening signal, such as North Africa or the East Asia. Yeah, thanks for your attention.
Thank you very much for that, and for being able to make it so it finishes just before 5. So congratulations, well done. I can see there's one or two chats coming through. I would like to say that this, well, I'd like to thank all the speakers. I'm going to stop the recording now, and so anybody who's got some time to stick around can maybe ask some questions and we can go through, but I'm going to press stop on the recording.